Okay, hard to believe, but here we are at the end of the semester. We're going to tackle Chapter 17, which is all about nuclear reactions and radiation. Quick review of atomic structure from back in, I think it was Chapter 5. Typical atom, you have your nucleus, which is made up of protons and neutrons. And the nucleus is surrounded by electrons. All the mass in the atom is locked up here in the nucleus. The nucleus is very, very tightly packed. Extremely high densities of material in the nucleus. You know that protons have a charge of +1, so your protons here have a charge of +1. Your neutron has a charge of 0. The electron, of course, is -1. When we're showing an atom, like uranium here, we have uranium-238. The 238 up there is the atomic mass. The 92 at the bottom is the atomic number. So you remember the atomic numbers are the whole counting numbers. 13, 14, 15, 16. Those are your, 13, 14, 15, 16. Those are your atomic numbers. So this is saying that sulfur, an atom of sulfur contains 16 protons, whereas an atom of uranium here, this atom of uranium contains 92 protons. Well, how many neutrons does it have? Hey, if you take the difference here, your 238, 238 minus 92, you'd say this guy has 146 neutrons. He has 92 protons. Notice, if you add these two up, you get the atomic mass. All that is review. Now, the identity of an element. What identifies an element? That one there. The atomic number identifies the element. So, uranium here. Here's our uranium. He's element number 92. Anything that contains 92 protons in the nucleus is uranium. Now, most of this course has been concerned with chemical changes, chemical reactions. In a chemical reaction, all you ever really do is you mess around with the electron cloud. As chemicals react, electron clouds tend to overlap and form covalent bonds, or somebody loses an electron, somebody gains an electron. So a typical chemical reaction might be you start with sodium. The sodium loses an electron. Do you see here that sodium now has one less electron, so the sodium takes on a positive charge. So that sodium lost an electron. But guess what? The number of protons and neutrons stays the same. In a chemical reaction, in chemical reactions, you do not mess with the nucleus. The number of protons and neutrons stay the same. In a chemical process, if you start off with an atom of sodium, you're going to end up with an atom of sodium. Now, nuclear reactions are going to be entirely different. In nuclear reactions, you start off as one element, but you end up as an entirely different element. It's weird. Anyway, quick review of isotopes. We talked about isotopes. You can have a whole series of isotopes for an element. They're all the same element. Here we have carbon 11, carbon 12, 13, and 14. Hey, carbon 12 here. Wow. On a periodic table, carbon is element number 6. So this guy has 6 protons and 6 neutrons. Carbon-13, he's a different isotope of carbon, but he's carbon. If he's carbon, he's got to have 6 protons. Carbon-14, it's carbon, so it's got to contain 6 protons. Carbon-11 will also have your 6 protons. If it's an atom of carbon, it must contain 6 protons. Now, the difference between them, this one's a little heavier. Why? He happens to have an extra neutron. This one happens to have 2 extra neutrons versus carbon-12. This guy here happens to only have 5 neutrons. Chemically, they all behave exactly the way carbon is supposed to behave. But they have different masses. They're different isotopes. Now, some isotopes are stable. So with our little series of carbon isotopes here, turns out carbon-12, carbon-13, extremely stable isotopes. Nothing happens to them over time. If you're an atom of carbon-12, a million years down the road, you're still going to be an atom of carbon-12. So these are stable isotopes. What about these guys? Carbon-11, carbon-14 are unstable. They are radioactive isotopes. So you'll hear these unstable isotopes referred to as being radioactive. Some people will call them radionuclides. So radionuclides, radioisotopes, radioactive isotopes. You get the picture. They kick out radiation. So let's say you're an atom of carbon-14. What happens to you? Well, at some point, as an atom of carbon-14, you're just going to change into an atom of nitrogen-14. Huh? How does that happen? I mean, let's see. Carbon has 6 protons. Nitrogen has 7. Does that mean that this thing picked up a proton from somewhere? Well, no, actually it doesn't. The way this happens, the way this nuclear reaction takes place, here's a picture of it from the book. Here's your carbon-14. He has 6 protons, those are the red ones. He happens to have 8 neutrons, and somehow in this process, one of those neutrons, like that one right there, that neutron turns into a proton. How did that happen? How did you go from being a neutron, a charge of 0, now you're a proton with a charge of +1? How did you become positive? You threw out, you cast off something that is negative. And that thing that's negative, he's got a charge of -1. He has no mass. That is an electron. So, the way the carbon-14 turns into nitrogen-14 is to spit out an electron here. That electron is sometimes referred to as a beta particle. And if you have a chunk of carbon-14, that chunk of carbon-14 is constantly spitting out these beta particles. That is a form of radiation. Now, just so you know, that electron, it's not a normal electron that's circling around in the electron cloud. He's not one of these guys that's just kind of gently circling the electron cloud. that beta particle, that guy is being spit out of the nucleus with quite a bit of energy. It's moving really fast. If it hits you, it's going to do some damage. You get hit with a stream of beta particles, beta radiation, it'll burn your skin. I think it can penetrate a couple of millimeters into your flesh and burn your skin. So it's not your typical electron. You know, after it hits your skin and it loses all its energy, it's going to be just another everyday electron. But when it first comes out of that nucleus, it is moving really fast. So you have different types of different types of radioactive decay that give you different types of radiation. Carbon-14 gives you beta radiation. It undergoes decay by spitting out one of these high energy electrons. There's also alpha emission. Alpha emission is when you have an isotope that spits out a helium nucleus. Picture that in your book. That very reaction here in your book would be this. You have some isotope, and for some reason, from the nucleus, it cleaves off a little chunk with 2 neutrons and 2 protons. See, there's your 2 neutrons and 2 protons. Well, from your periodic table, that's helium. Helium contains 2 protons. He's got an atomic mass of 4. So 2 protons, 2 neutrons. Oh yeah, it's a helium nucleus. So some things, when they decay, they just spit out a helium nucleus. That one's referred to as an alpha particle. And this would be alpha decay. You'd say this isotope decays via alpha decay. And if you had a chunk of this isotope, you had a big old lump of it, this would be going on, and you'd get a constant stream of these alpha particles coming off of the material, and you'd be getting hit with alpha radiation. So you can have alpha radiation, which is a helium nucleus. You know, beta radiation, which is a stream of high energy electrons. Oh, by the way, you'll see 2 different notations used. Chemists tend to show alpha particles this way. Physicists tend to just write the little symbol alpha. Chemists, we tend to show beta particles this way because we think of them as electrons. Physicists will use that little thing for beta radiation. Now, other types of radiation exist. There's positron radiation, where a material is kicking out a stream of so-called positrons. Here's an example of that. You don't have to worry about this one. It's pretty rare. But this particular isotope of potassium will spit out what's called a positron. What's that? It's a form of antimatter. It's the opposite of regular matter. So that positron is an electron. It's an electron that carries a positive charge, hence a positron. There's electron capture. Again, I wouldn't sweat that one too much. Now, all these types of radiation have different properties. You should have some grasp of how dangerous they are. When you're talking radiation, you always want to consider 2 things. How much damage is the thing going to do when it hits you? That's usually referred to as its ionizing power. How much capacity does this have to damage human tissue? And then there's also penetrating power. How far into the body can that radiation go? Alpha radiation is interesting. It's got very high ionizing power. It can do a lot of damage to your cells. It can cause cancer, can kill cells. Here's the deal. It has virtually no penetrating power. You can stop alpha particles with a sheet of paper. They won't penetrate through a sheet of paper. They like to say you're protected from alpha radiation by dead skin cells. Your skin has a layer of dead skin cells on it. This thing can't get through the layer of dead skin cells. Now, materials that are alpha emitters, like this uranium-238, as long as it stays outside of your body, you're okay. This stuff's not going to penetrate. If you, say, inhale some uranium dust, well, that uranium dust gets stuck in your lungs over the course of years. It's constantly putting these out, and these will do a lot of damage to your lungs and quite likely cause cancer or something. Now, beta radiation, these beta particles, not as ionizing. They're kind of moderately ionizing. They can do some damage, and here's the thing, they will penetrate a few millimeters into your skin. They can make it through aluminum foil, probably through a couple of millimeters of aluminum foil. They'll just go right on through. Positron radiation, pretty dangerous, because this is antimatter. As soon as this thing hits another electron, the two are going to annihilate each other, give a big burst of energy and some extra radiation. So, one more type of radiation we have to talk about, and that is gamma radiation. Sometimes when things decay, they give off your alpha or your beta, what have you, and they also give off gamma radiation. Gamma radiation, how many protons is it worth? 0. How much does it weigh? Nothing. Gamma radiation is electromagnetic radiation. We talked about the electromagnetic spectrum way back. So this is electromagnetic radiation. It's energy traveling at the speed of light through the universe. It's got an extremely short wavelength and extremely high energy. In my notes here I go into some extra explanations of it. Don't worry about that. Just understand gamma radiation, nasty stuff. This is very penetrating. Gamma radiation can penetrate through a couple of feet of concrete. And gamma rays will typically kill most things they hit. You get hit with a good dose of gamma rays, you're toast. So gamma radiation, very dangerous. Now, quick thing to go over here, probably the most important part in this chapter, the part that you'll see on the final. Completing these nuclear reactions, and hopefully you've noticed, although they're really weird, you start with one element and you end up with a different element. There's still an element of balance here. If I add up all the bottom numbers here, it's got to add up to that bottom number. You see, 90 plus 2, 92. However many protons I have on this side of the arrow, I'd better have that many protons on this side. They also have to mass balance. So if I add up all the top numbers, all the mass numbers, let's see, my alpha particle has a mass of 4. My thorium here, 234. That adds up to 238. They always have to balance out. If you look here at this one where the thorium decays, let's see, -1 plus 91 is 90. 234 plus 0 is 234. And you can check with these other ones here. All those numbers have to balance out. So the types of problems you'll have to be working will be similar to these here. You see some kind of nuclear reaction and we ask you what's the missing particle. So this is This is a nuclear reaction involving magnesium, and that magnesium is absorbing a proton. It's giving you an alpha particle. Keep in mind that alpha particle is helium. And it's asking, what's the missing thing? What's the other element? How do you do this? Well, if we add this up, 26 plus 1, we know that all the top numbers have to add up to 27, right? So 4, this has to be something with a mass of 23, because you see 23 plus 4 adds up to same thing as 26 plus 1. So whatever this is, it's got a mass of 23. How about the bottom number? The bottom number is important in that the bottom number, remember the bottom number is the atomic number. That tells us what the element is. So let's see here. I got 12 plus 1 is 13. So this bottom number has to be 11, because 11 plus 2 is 13. What element has an atomic number of 11? Oh, sodium. Yes. So the missing particle in this reaction is sodium 23. Let's take a look at the next one here. You have oxygen 20 turning into fluorine 20. So the mass did not change. 20 on top, 20 here. So whatever this is has a mass of 0. 8. So 9 plus whatever this is had better equal 8. Oh, that's negative 1. What type of thing has no mass and has a charge of negative 1? The electron. So it's a beta particle is the missing particle on that. So that's how you complete these nuclear equations. My notes here, I'm kind of skipping some sections. Just so you know, if you do end up doing some stuff with nuclear, there are what are called decay series. These elements don't just typically undergo one-step decay. Sometimes uranium here, it decays to make thorium. That thorium is radioactive, and it eventually decays to make some more uranium, which decays back to thorium, which decays. So you can have a whole series of nuclear reactions. It's not like one decay happens and then the stuff is safe. Sometimes you have a whole series. That's called a decay series. Okay. Let's see. We should very, very briefly talk about half-lives. Anytime you're handling radioactive material, you worry about the half-life of the material. The half-life is simply how long it takes for 50% of the atoms in that sample to undergo decay. Half-lives can be incredibly long. Like your thorium here has a half-life of 10 to the 10th years. That's like 14 billion years. So if you have a sample with, say, 100 thorium atoms, you got 100 of these, well, 14 billion years later, instead of having 100, you'll have 50. 50% of them have undergone decay. Now, other things, this one here, thorium-219, has a half-life of milliseconds. So in 1 millisecond, 50% of these atoms will undergo decay. Real quick, shorter half-lives are more radioactive materials. If I had a choice of having a chunk of this under my bed or a chunk of this, I'd go with this one. I mean, chances are nothing's going to happen all day long. None of these atoms are going to decay. It takes 14 billion years for half of those atoms to undergo decay and spit out their radiation. You had some of this under your bed, in 1 millisecond, they're all going to undergo decay, they're all going to kick out their radiation, and you're going to get fried. This is a much hotter material, so shorter half-life is hotter. And again, half-life is simply how long it takes for 50% of the atoms to decay. If you started with 1 million atoms, 14 billion years later, you'd have half as much. Wait around another 14 billion years, you've got half as much as you did a moment ago. So that's half-life. Hey guys, wish I could go into a lot more detail with nuclear, but sad to say, this is pretty much the end of your intro chemistry class. Before I leave you here, I do want to go back to the very first day of class. Very, very first day of class, I told you that chemistry is all about chemical reactions. And I showed you this demo. We started with silver nitrate dissolved in water, and it was all colorless. We dropped in a copper wire, which was brown. 10-15 minutes later, we ended up with shiny silver metal. So this silver metal was coating the brown copper wire, and the liquid, instead of being colorless, was now blue. So in case you forgot it, it looked kind of like this. Oops. That's that test tube we used for the demo way back when. Here's the nice brown copper wire. You can see some of the silver metal here, that shiny gray stuff. That's metallic silver. The blue liquid is the copper nitrate. So anyway, I hope you've learned something over the semester about chemistry. I hope I helped you out in your next class. One last thing to tell you, when we went through chemical reactions, we didn't classify this one. We had precipitation reactions, acid-base reactions, combustion. This type of reaction is known as a single replacement, or sometimes single displacement reaction. What's that about? Oh, you have a metal hooked up with something, and this metal, basically, this metal replaces this one. So instead of silver nitrate, I end up with copper nitrate. So again, that's referred to as a single replacement. Some people say single displacement reaction. It's just another category of reactions, and we had never really talked about them in depth. Anyway, guys, again, that wraps up Chem 1120. Really sorry that we didn't have time to complete the class face-to-face. Thanks for putting up with these videos. I know that the video quality has been shaky. I know the audio has been horrible. Sorry, I haven't been able to fix that. Start working on that final exam that I posted last week. I'll send that out I'll send out a message about that in the email. Guys, stay safe out there, stay healthy, and good luck in the future.